channel. I'm Ome Chukwuemeka, and I've done part 1 of this Bitcoin theory. This is the part 2, so welcome back to the part 2. Make sure you watch what is blockchain and then watch the part 1 of Bitcoin theory before you can be able to understand this part 2. Alright, remember I'm doing this video tutorial for my students in the NITDA Blockchain Scholarship. So specifically targeting Ebonyi State participants in the program. Right, so we'll be having a lot of fun. And remember to also subscribe to my channel, and if you have any questions, leave it in the comment section and I'll be able to attend to you. And then if you have further challenges whatsoever, let me know, either in our WhatsApp group or in our Telegram channel or privately, personally, and then I'll be able to help you sort it out. All right, so if you have gone through the first video, that's the part 1, we stopped at timestamp server. So we're going to start from number 4, which is proof of work. All right, I'm doing my best to explain this in greater detail, and so that you can be able to understand what Bitcoin is all about. All right, to implement a distributed timestamp server, this distributed timestamp server is just a distributed ledger. Remember that, it's just a ledger, and it's a network, a ledger. That's like I explained in what is blockchain. Now, to implement this on a peer-to-peer basis, we will need to use a proof of work system similar to Adam Back's hash cash, rather than newspaper or Usenet post. So let's see what this Adam Back's hash cash is all about. Let's copy it and see what it's all about. So what is this? So let's see. Adam Back is a Bitcoin entrepreneur and computer scientist who has been involved in the cryptocurrency industry since its early days. He is best known for inventing Hashcash, a proof of work system used to combat spam and denial of service attacks, which is also used by the Bitcoin network. Okay, what is Adam Back Hashcash? Where is it used in Bitcoin? Hashcash refers to a proof of work system that was created by Adam Back in 1997. His creation was initially meant to limit email spamming. If you have been receiving spams on your email, and then DDoS attack means denial of service attacks, means like once denial of service attack means when too many computers are trying to access your website, it just goes offline. It overloads it, it goes offline. Okay, in more recent times, however, the system became popular for its involvement with Bitcoin, another cryptocurrency, as an essential piece of the mining algorithm. Means that it helps to make sure that the server is always on, it doesn't go offline. The server is always on. That's what this is about. All right, so we may not go into greater details about it other than what I just explained. Now, rather than a newspaper or Usenet posts, means a post is just like a normal URL on maybe a website you are visiting, maybe on Vanguard or Top Trends Nigeria or Sun newspaper or which other one, Guardian newspaper or Tribune, some things like that. The post they make, there can be a denial of service attack on it. Means the server can be overloaded, and then boom, it goes offline. You can be able to access it. Now, the proof of work involves scanning for a value that, when hashed, remember what I explained here. Let me get back here. This, remember what I explained here, if you can remember, turning this into a long character. So that's what is being said here. It says the proof of work involves scanning for a value that, when hashed, such as with SHA-256. The hash begins with a number of 0 bytes. Just understand it as characters. The average work required is exponential in the number of 0 bytes required and can be verified by executing a single hash. It's just trying to explain to you how the hash is being done. Alright, how the algorithm hashes it, how it turns a text like this into a longer character. Now, for our timestamp network, we implement the proof of work by incrementing a nonce in the block until a value is found. Remember, this key is random. Okay, you have to use an algorithm to keep finding it. Okay. Now, nonce in the block until a value is found that gives the block's hash the required 0 bytes. The required 0 byte means it's just required. Remember, bytes is just zeros and ones. I think in one of our online classes, I was trying to show you, we did an addition of 5 plus 6, which gives us is equal to 11. All right. And I explained to you about the operating system, the assembly language, and high-level programming language, and then low-level programming language. I explained to you that. Now, let's turn this into binary numbers, 5 into binary numbers. So let's say, allow me to close this, 5 into binary number. Let's see what it gives us. 5, you see, 5 is 101. Okay, let's say 101 plus what of 6? 6 is what? We have 6 already. 110 is now equal to 11. Is what now? 11 into binary number is what? Remember, 1011. So we have it as 1011. Remember that I explained to you that this ones and zeros is on, 1 is on, 0 is off. Current is passing through your motherboard, the motherboard of your computer. Okay, as its current is passing through it, the computer is designed with semiconductors. Your chip, the microchip, that's the processor, is designed with semiconductors. Okay, the P and N type semiconductors. I wouldn't want to go into much details about that, but then remember that electricity is flowing through your current to your laptop to generate this. So as it flows off, on, off, on. Example for 5 is once it does on, off, on means it's 5. Once it does on, off means it's 6. Once it does on, off, on means it's 11. Now in our material, Bitcoin theory material, you see, to implement the distributed timestamp server on a peer-to-peer basis, we will need to use a proof of work system similar to this, all right, rather than this. Then proof of work involves scanning for a value that, when hashed, such as these characters, 256 Latin characters, the hash begins with a number of 0 bytes, means there's a number of zeros it has to start with. 0, 0, zeros. It could be specified, but I didn't see it here. Now the average work required is exponential. Exponential means multiplied by a particular number, especially in the number of 0 bytes required. So if the 0 bytes is required, the number of 0 bytes required is 10, then you have to multiply this by 10. All right. So it's saying begins with a number of 0 bytes. The average work required. So let's say it could be that the number of 0 bytes is 3, and then we begin to have our ones, another characters, E, small e, capital F, and stuff like that, so until it satisfies this 256 SAH. Now the exponential has to be, we multiply the entire thing by number of 0 bytes, which is 3. Exponential raised to power 3. That's what it means. Now, let's get back to it. I know you may have questions, but then just drop it in the comment section and I will attend to you, okay? Now, the hash begins with a number of 0 bytes. The average work required is exponential in the number of 0 bytes. This is trying to find the key, remember, the key to change the transaction that has been verified. Required and can be verified by executing a single hash. Means those who are competing to change this transaction into the chain, to add this transaction into the chain, and then broadcast it in the distributed ledger, will have to carry out this. So it's more. This is a more detailed process of the whole stuff. I explained in what is blockchain. Okay. For our timestamp network, we implement the proof of work by incrementing a nonce. Nonce should be 1, I think. What is nonce? Let's check it out. Nonce in blockchain. Nonce, a word coined for one occasion. It means 1. So let's say what is nonce in blockchain. Let's see. Within several proof of work blockchains, including Bitcoin, a nonce is a random 32-bit number. See now, that miners use as a base for their hash calculations. Means they use this nonce to be able to find the random. So what that number 4 is trying to talk about is trying to tell us how this key is found, the processes in which it is found. So you have to be able to be careful about the keywords you are hearing or reading about. So you've seen what nonce is in blockchain. Within several proof of work blockchains, including Bitcoin, a nonce is a random 32-bit number. Remember that there are other blockchains that doesn't require proof of work. I think Stellar Lumens doesn't require proof of work, for example. Now, that miners use as a base for their hash calculations. Miners compete with each other, trying to get a valid nonce, means finding that key as they attempt to calculate a block hash. As they attempt to calculate it and then add it. That's what it's just all about. So, for our timestamp network, we implement the proof of work by incrementing a nonce. Once they increase it by 1, which is 32 bits, they increase it by 1 in the block until a value is found that gives the block's hash a required 0 bytes. There's a required 0 byte it has to get to before it is valid. So the first computer that finds it, the required 0 bytes, gets a financial reward. Remember that I explained this in what is blockchain. Gets that financial reward, in this case Bitcoin. Now, once the CPU effort has been expended to make it satisfy the proof of work, the block cannot be changed without redoing the work. Means it cannot be added, it cannot be changed. What has been added cannot be removed. That's basically what it is. It cannot be removed unless you have to redo the entire transaction, and by that time the entire transaction is over anyway. Has been concluded because it has been broadcasted to other networks, other nodes who now have it in their distributed ledger. All right, that's what makes Bitcoin safe, because once it's done, it's done. That's why sometimes when you lose your Bitcoin, you have lost it. Okay, now once the CPU effort has been expanded to make it satisfy the proof of work, the block cannot be changed without redoing the work, as letter blocks are changed after it. You see, as letter blocks are changed after it, the work to change the block would include redoing all the blocks after it. You see, so once it is changed, for instance, you want to redo this particular block, for instance, it can be changed, because for you to redo this work, you have to now redo all this other block, all these subsequent other blocks of transaction. You get now? So this is it, a block, previous block, the nonce. Remember the nonce. Remember the principle behind it. It has to be exponential based on the number of required zeros. So the first CPU to find that required zeros has won the competition between miners. Now the proof of work also solved the problem of determining representation in majority decision making. If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. That's why many miners, they are competing. Remember, this is a network. You see IP coming in, an IP address. You can just check your own IP address if you're in your browser. Let me close this. So what is my IP address? My IP. It will bring up my IP for me. This is my IP address, current IP address I'm using. The IP address can change anyway. So this is what an IP address looks like. So you can check that for your own. It will be different number from my own. All right. So proof of work also solve the problem. Now, if a majority of CPU power is controlled, okay, where was I? Now, if the majority were based on one IP address, one vote, it could be subverted, means it can be changed by anyone able to allocate many IPs. Proof of work is essentially one CPU, one vote. The majority means that one CPU, one IP address can only find one key, not at a time anyway. After a miner successfully finds the IP, it can go for the next transaction and begin to look for the random key. All right, but you cannot be looking for two keys at the same time. That's just basically what he's saying. The majority decision is presented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest node, the honest chain will grow the fastest and outpace any competing chains. To modify a passed block, an attacker would have to redo the proof of work of the block and all the blocks after it, and then catch up with and surpass the work of the honest node. Means that an attacker, for instance, will have to take, for instance, if they want to branch out a chain, they will have to redo a particular block and then redo all this other block. To outpace it, the probability is very small. That's where the calculation comes in. All right, we'll get to that section. So they have to keep doing it until they outpace this honest node. And this honest node is a group of various IP addresses, various miners. All right, so an attacker has to also get more IP address to surpass this particular one. You get the point now? And to do that is hard. The person has to keep looking for all these keys, it's hard to do. That's why blockchain is an amazing technology. Okay, now if a majority of CPU power is controlled by honest node, the honest chain will grow the fastest and outpace any competing chains. To modify a passed block, an attacker will have to redo the proof of work. Proof of work, remember, is just to find that random key, and the principles of finding a random key is, we've checked it here about the ones and the zeros before it and the exponential of those things, and then hashing it. Remember that we found it, we explained it here. Now, to modify a passed block, an attacker would have to redo the proof of work of the block and all blocks after it, and then catch up with and surpass the work of the honest node. We will show later that the probability of a slower attacker catching up diminishes exponentially as subsequent blocks are added. As other miners are finding keys, random keys, and adding transactions to the chain of blocks, it's trying to tell you that that's where the calculation comes in. It diminishes exponentially. An attacker will find it hard to be able to surpass the honest nodes, to surpass the honest miners. Now, to compensate for increasing hardware speed and varying interest in running nodes over time, the proof of work difficulty is determined by a moving average, targeting an average number of blocks per hour. If they are generated too fast, the difficulty increases. Means the timing, or it becomes hard as more miners are trying to find these random numbers. The difficulty of finding that random numbers increases by average by half. All right, what it means is it becomes half more difficult. No, sorry, and half is added. Then, for instance, if difficulty of finding a key is, let's say, 2, for instance, as more miners join in trying to find this key, the difficulty becomes half of this. More like it becomes half is now added to this. So half of 2 is what? 1. So 2 plus 1 is what? 3. So the difficulty increases to 3. That's what that comment means. To compensate for increasing hardware speed and varying interest. Varying interest means other miners trying to run nodes over time, special nodes trying to mine. The proof of work difficulty is determined by a moving average. Average means half, targeting an average number of blocks per hour. So how many blocks are found per hour? is targeting it. So if the blocks found per hour is very much, it begins to increase the difficulty. If they are generated too fast, the difficulty increases. It's just that simple. All right. The steps to run the network are as follows. New transactions are broadcast to all nodes. You see now, new transaction. I explained this in what is blockchain. So you broadcast the transaction. Each node collects new transactions into a block. Each node works on finding each node works on finding a difficult proof of work for each block. You see, when a node now in this case, whoever is the first to find it finds a proof of work, it broadcasts the block to all nodes. Means it sends the information. It doesn't store it in a database, it just broadcasts it, sends it to them. Is that by the way to understand this broadcast is like text message. Text message is stored in each of their following, in each of them, each of the nodes. Like text message now, once it's sent to you, it's not stored. It's stored in your phone. It's sent and it's stored in your phone. Once the other person deletes it from their own end, it's still in your phone. You get now. So it's on the network. It's sent peer to peer. That's what it's all about. Okay. Now nodes accept the block only if all transactions in it are valid. You know what it means to verify a transaction. To validate a transaction means that the person has enough money to send. All right. And they are not already spent, means that they shouldn't be sending what they have already spent. And the last step is nodes express their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block as the previous hash. Means it has been added to the chain. Other people will update their distributed ledger. It's just that simple. Right? That's how the network works. Remember now, there's no database mentioned here. Nodes always consider the longest chain to be the correct one. Remember that, the honest node and the attacker node. And we keep working on extending it. If two nodes broadcast different versions of the next block simultaneously, see now, some nodes may receive one or the other first. In that case, they work on the first one they received, but save the other branch. This is like a branching, remember that. They will save it. They save the other branch in case it becomes longer. The simple thing is this. What is here is also what should be here. That's just it. So if what is here is not here, then this is irrelevant. So the attacker node has to grow. Remember that. Once it keeps growing, it means, remember, it has to redo these other blocks of transaction in order to add it to itself. I think I've explained that. And then keep growing. So there are so many branches that can be coming out. So it's saying that if a branch is created and they form the two blocks are at the same level. Let's say now there's a block here and there's another block here. It's just the same. What will happen? The nodes will save the ones they received first, and then begin to work on it while they keep a copy of the other one, and then keep watching to find out which one grows faster than the other. Whichever one grows faster than the other, they'll switch to it. They keep updating the chain. That's what it's all about. All right. In that case, they work on the first one they received, but save the other branch in case it becomes longer. The tie will be broken when the next proof of work is found, and one branch becomes longer. You see now, the nodes that we are working on the other branch will then switch to the longer one. You see, the nodes which are the miners. Nodes is just miners. New transactions broadcast do not necessarily need to reach all nodes. As long as they reach many nodes, they will get into a block before long. Block broadcasts are also tolerant of dropping messages. If a node does not receive a block, it will request it when it receives the next block and releases its missed one, and realizes it missed one. Remember that. It's just like I'm talking about updating the distributed ledger. That's just it. Okay. Incentive. Now that's where we've gotten to incentive number 6. By convention, the first transaction in a block is a special transaction that starts a new coin owned by the creator of the block, which is the Genesis block. Genesis means the initial transaction allocated. This adds an incentive for nodes to support the network and provides a way to initially distribute coins into circulation. Since there is no central authority to issue them, The steady addition of a constant of amount of new coins is analogous to gold miners expending resources to add gold to circulation. In our case, it is CPU time and electricity that is expended. That more like it's used to add coins into the blocks. The incentive can also be funded with transaction fees. You see, transaction fees. When you're trying to send a coin, you pay transaction fee. Like Bitcoin, you pay certain percentage on transaction fee, and that's what they give to people who are mining as their incentive. If the output value of a transaction is less than its input value, the difference is a transaction fee that is added to the incentive value of the block containing the transaction. Once a predetermined number of coins have entered circulation, the incentive can transition entirely to transaction fees and be completely inflation free. So just pure economics on how to manage money in the economy or money circulation. The incentive may help encourage nodes to stay honest. Means they don't want to branch out and start creating problems for the blocks. If a greedy attacker is able to assemble more CPU power than all the honest nodes, he would have to choose between using it to defraud people by stealing back his payments or using it to generate new coins. You see, that's dangerous, but it's not possible in blockchain. Why is it not possible? Because so many honest nodes have more CPU power and more IP addresses than an attacker. Far an attacker will be able to assemble people to be able to join him. It's going to take time. That's just the truth. He ought to find it more profitable to play by the rules, such rules that favor him with more new coins than everyone else combined, than to undermine the system and the validity of his own wealth. Now, 7, reclaiming disk space. Once the latest transaction in a coin is buried under enough blocks, they spend transactions before it can be discarded to save disk space. This is what's just happening in the network. More like once you have sent a text message, you can just delete it from your own end because you've already sent the message. You just it. That's just as simple as that. To save your own phone memory. I'm using that for example. Alright. To facilitate this without breaking the block's hash, transactions are hashed in a Merkle tree. So what is a Merkle tree? So let's find out. So remember that this is a detailed explanation of what I said in what is blockchain. What is Merkle tree in blockchain? Merkle tree is a data structure that is used in computer science application in Bitcoin and other cryptocurrency. So let's use what is Merkle tree in blockchain. Merkle tree is a data structure that is used in computer science application, Bitcoin and other cryptocurrency. Merkle trees serve to encode blockchain data more efficiently and secure, just like storing the data. To encode it, they are also referred to as binary hash trees. Look at the way it just is Merkle. You see, just like this. To encode the data, to hash it. You see the picture diagram? Just like encrypting a password. That's just what it is. Right? So where are we? With only the roots included in the block's hash, old blocks can then be compacted by stopping off branches of the tree. You see, the interior hashes do not need to be stored. That's just what we saw in that picture. Remember that? So you just keep storing it like this, hashing it. A block, this is under reclaiming disk space, okay? Like I just explained it in the principle, it's just like sending someone a text message and then you delete that text message from your own end. Or you try to save that text message, copy it and save it somewhere. That's what it's just about. Okay? A block header with non-transaction would be about 80 bytes. Remember that data structures is just like the way you arrange your information in computer science, or when you're working with data structures and algorithm, when you're writing codes. And some of you don't have knowledge of programming, so I'm trying to find a better way to explain this for you so you can grasp the concept. So that's why I used the issue of use the description of sending a text message to someone. All right. I don't want this video to be too long, but let me see where we are. we are getting to 8, so we'll have to find a way to get to, I think, 8. Then we'll stop the video and I'll upload it. Okay, now let me just finish this 7. So let me finish 7, then we'll start continue from 8. Okay, and to facilitate this, where am I? A block header with no transactions would be about 8 bytes. Don't worry yourself about this jargon, but you can do well to memorize this. If we suppose blocks are generated every 10 minutes, 8 byte times 6 times 24 times 365 equals to 4.2 MB per year. With computer systems typically selling with 2 gig of RAM as of 2008, and Moore's law predicting current growth of 1.2 gig per year, storage should not be a problem, even if the block header must be kept in memory. Let me stop here for now. In part 3 of the video, we'll continue from this. Alright, make sure you subscribe to my channel, and make sure you watch the part 1 before you watch the part 2. Before even watching the part 1, make sure you watch what is blockchain, so you can understand the entire concept. Alright, thank you so much. See you in the next class. Bye.